So the last thing we're going to look at with hybrid orbital theory is expanded octets. So these are going to be compounds that are going to utilize their empty 3D orbitals to hybridize and make more than 4 bonds. So third period central atoms. So these are going to be atoms in the third row. Can hybridize their 3D, just kidding, 3D orbitals in order to have an expanded octet. So remember that there are no 2D orbitals. So that means that anything in the second row cannot have an expanded octet. Okay, so we always say that carbon and nitrogen and oxygen always obey the octet rule. And it's not because they're like really good at following the rules. It's because they don't have any 2D orbitals because they don't exist. And so they can't expand their octet even if they wanted to. Okay, so let's see how this works. We're going to do PBr5. Okay, so we got phosphorus has got 5 valence electrons. And so we're going to do the 3s. We're going to do the 3p, and we're going to put in the 3d. Okay, so we got the 3s has 2 electrons, and the 3p has 3 electrons. Now we see that because if we draw this out, we have PBr5. That's going to mean that we have 1, 2, 3, 4, 5 electron groups, which means we need 5 hybrid orbitals. If you look here, we have 5 electrons, so that's good to go. Because remember, for this to work, we need to have an electron in a singly occupied atomic orbital of phosphorus. So we have 5 electrons, that's a good thing, but we don't have them in 5 different orbitals. And so what we can do is we can promote the 3s electron up to the 3p. So we end up with our 5 electrons all in different atomic orbitals. And so now we can hybridize. So when we do this, so if we hybridize, we're going to get 5, 1, 2, 3, 4, 5, sp3, and then we used 1 d orbital, so sp3d, and then we still have 4 unhybridized 3d, so we have 1, 2, 3, 4, 3d, and technically this is 3sp3d, though we generally refer to it as sp3d. Principal quantum number doesn't matter more than just saying what the energy is. So then we have in each one of these 1 electron, and so we can then say, if we want to say what is the hybridization on the central atom, we would say that phosphorus is sp3d hybridized. Okay, so if we were to do this and look at the bromines, so let's just draw this out real quick. I think it's useful to see. If we have phosphorus, phosphorus is going to have 1. I'm just going to kind of draw it, not in 3 dimensions. It's a little harder when you're doing these. Let's kind of equally space them. And these are all sp3d. Write those out. And then for bromine, we haven't gone over this. So for each one of these bromines, and we're going to, while we have we'll do electron in each from the phosphorus. For bromine, Bromine has, if we look at bromine, let's do bromine in blue. It has 1, 2, 3, 4 electron groups. So this is the first time we're not using a hydrogen here as attaching onto the central atom. So if we're going to hybridize bromine, it has 4 electron groups. Each lone pair is considered a electron group. So we're going to have sp3 hybridization of all of these orbitals. Even though the lone groups aren't a part of bonding, we're still going to hybridize it. So we would say that for bromine, oh, I guess we're going to do it in blue, I think. Yeah. So for bromine, this is sp3, bromine sp3, bromine sp3, and all the way around sp3, last one. Okay, and that's how you would draw the hybrid orbital diagram for PBr5. Now, a good follow-up question would be, here's a follow-up, can phosphorus make 6 bonds, or would you expect phosphorus to make 6 bonds? And if we go back and we look here, we can see that, remember, for using the hybrid orbital model, every bond requires an electron in its own atomic orbital. Well, phosphorus only has 5 valence electrons, so it can't make more than 5 bonds using this model. So we would say, no, only 5 valence electrons. And we're probably not going to promote a core electron up into a valent orbital to allow for that to happen, so we're going to say no. But you know who does have 6 electrons is sulfur, so we've already drawn this before, SF6, but we can see here that if we have the 3s, so this has 6 valence electrons, sulfur does. So 3s, 1, 2, 3, 3p, and then 3d is 1, 2, 3, 4, 5. We have 1, 2, 1, 2, 3, 4. 4 electrons. And so what we're going to do is we're going to promote 1 electron here and 1 electron here. And we're going to draw those in. And we can hybridize to give us, now we're going to need 6. 1, 2, 3, 4, 5, 6. These are all sp3d2. Some people might put d2 sp3. They're generally wrong. We tend to see it sp3d2, but don't be confused. All the information's there. So we have each electron in one of its 6 hybridized atomic orbitals, sp3d2, and then we would still have 3 unhybridized 3d orbitals, but no electrons in them. And if we were to draw this out, we would have S 1, 2, 3. Well, it would be, we would, so if we're, let's first do this. If we were to just draw out the Lewis structure with the fluorines, we would say that the hybridization on this would be sp3d2 hybridized. Okay, so that's how we can use hybrid orbital theory and this idea of experimental octets to explain why we can have these hypervalent compounds or compounds that are going to expand past an octet. Okay, so and you'll notice in both cases we're taking something that's not as electronegative, so third row, and then bonding with something, especially like fluorine, that removes some electron density. So that's hybrid orbital theory, very conceptual in nature, and then we're going to move on to molecular orbital theory, which is very mathematical in nature, but we won't do much of that math in this class.